equations involving radicals can often be solved by transforming them first into more familiar first and second degree equations without radicals. Let me give you an example. Let's start with something very simple. The square root of x equals 4, an equation involving a radical, the square root of x here. To solve this, we can square both sides of the equation, and in doing so, we get the square root of x squared equals 4 squared, or x, the square root of x squared just leaves us with x, equals 16. Let's check and see if we actually have found the solution to the original equation. We start in the original equation. The square root of x is equal to 4. We believe that x equals 16 is a solution. We substitute in the square root of 16 should be equal to 4. Remember, when it says the square root of 16, this means the positive square root. Okay? There is a plus implied here. The positive square root of 16, of course, is equal to 4, and it checks out. Let's try another example. The square root of x is equal to minus 4. If we follow the same procedure and square both sides of this equation, we get x is equal to 16 as a possible solution. However, if we try to go back to the original equation to check it, the square root of x equals minus 4, we substitute in x equals 16, we get that the positive square root of 16 should be equal to minus 4. But of course, 4 is not equal to minus 4, and this is not a solution. Okay. So we can cross that out. Now let's see what went wrong here. Well, there is some good and bad news about squaring both sides of an equation. The good news first. You will not lose any solutions of the original equation. If you start with an equation involving radicals, like a square root, if you square both sides of the equation and you solve the resulting equation, okay, if you solve the resulting equation, any solution to the original equation will also be a solution to the new equation. Okay, now the bad news. You might get some extra solutions that you didn't count on. You might, in squaring both sides of an equation, you might introduce additional extraneous solutions, solutions to the squared equation that are not solutions to the original equation. So while you will not lose any solutions, you might get a few extra, which means this checking business is very important. Okay? You won't lose any solutions. So you square both sides of the equation, you get solutions, at least what you think are solutions. You then check each one in the original equation. Now, if you've done things correctly, they're all going to be solutions of the squared equation. The question is, are they solutions to the original equation? So go back to the one with the radical, substitute in. If it works out, then you have found the solution to the original equation. If it does not, then you haven't. Of course, we can see here the problem is that this original equation has no solutions, no real solutions here. How can the positive square root of x be negative 4? Regardless of what x is, positive square root is not going to be equal to a negative number. The problem is that when you square both sides of an equation, you don't necessarily get an equivalent equation. If you start with a true statement like 3 equals 3, and you square both sides, you get, of course, 9 equals 9, which is also a true statement. However, it's quite possible to start with something like minus 4 equals 4, which of course is not true, square both sides, and get a true statement. Okay, this is true, squared, it's still true. We start with something that's false, squared both sides, and we got something that's true. And this is the problem. In squaring both sides of an equation, you do not necessarily get an equivalent equation. Okay, all this means from the practical point of view is that you must check every solution that you get to the squared equation to make sure it's really a solution to the original equation. Okay, let's try some more examples. Now, very often the checks will work out, but sometimes they won't. And just for those cases when they don't, you have to be careful all the time. This, by the way, is true whenever squaring both sides of an equation or, in general, raising both sides of an equation to any even power. If you cube both sides of an equation, you don't have to worry about extraneous solutions. Just if you raise both sides of an equation to an even power. Okay, let's work this out. The square root of 4x minus 3 minus 2 is equal to 3. Here we have a slightly more interesting radical equation. Okay, let me start by showing you how not to do this problem. Okay, the wrong way to do it. Okay, because many of you will think of doing it this way. The wrong thing to do is say, well, look, I'm going to square both sides of the equation and say, well, I'll square this and get 4x minus 3, and I'll square the minus 2 or something and subtract it and get this. This is wrong. Okay, this is not how we square both sides of an equation. This is not the proper thing to do. And making this a plus 4 wouldn't help. That's not what's wrong. What's wrong is that you were dealing with something here like a minus b. And when you want to square a minus b, it is not a squared minus b squared. If you think of all of this, say, as a, and this, say, as, minus b. To square this, we're squaring both sides of the equation. You just simply square this and square that. That is incorrect. It's not this number squared minus this number squared. This is not how we do it. What is a minus b squared? It's a minus b times a minus b, and by FOIL, it's a squared minus 2ab plus b squared. Okay, so this is an incorrect procedure. Let's start the problem all over and do it the correct way. Solve for x, and here we start with the radical equation. The square root of 4x minus 3 minus 2 equals 3. Since squaring both sides of the equation as it stands right now will not eliminate the radical here. Okay, see, the problem is you have like a minus b to be squared. So you'll get this squared and this squared, but you'll get 2 times the product of these terms, and of course that will still involve a radical. So instead, what we do, and this is a trick to use whenever you're trying to solve a radical equation, first isolate the radical. Okay? Isolate the radical. By that I mean get it alone on one side of the equation. This is the main trick for solving radical equations. Isolate the radical. Okay, so before I actually square both sides of the equation, what I'm going to do is add 2 to both sides of the equation. Okay, so I add 2, and that gives me the radical alone on the left side. The minus 2 and the plus 2, of course, drop out. And on the right side, I have 5. So I've added 2 to both sides of the equation. The object was to isolate the radical. It should be alone on one side of the equation. Now you square both sides of the equation. When you square the left, the radical will drop out. The square root of 4x minus 3 squared, that's just 4x minus 3. 5 squared gives you 25. You solve the equation now. You add 3 to both sides. 4x is equal to 28. Divide both sides of the equation by 4 to get a possible answer of x equals 7. And in a radical equation like this, when I've squared both sides, at the moment, the best I can say is that it's a possible answer. I must check to make sure that it is actually a solution to the original equation. Check. And don't forget, you go back to the original equation as it was given to you, the square root of 4x minus 3 minus 2 equals 3. Not after you've squared it, not after you've altered it in any way. Always go back to the original one. We are trying to check the value x equals 7. We believe that this will give us a true statement. Let's substitute it in. The square root of 4 times 7 minus 3 minus 2 should be equal to 3. The square root of now 28 minus 3 minus 2 should be equal to 3. The square root of 28 minus 3, that's the square root of 25 minus 2, should be equal to 3. The square root of 25, of course, that's 5. It's the positive square root of 25. 5 minus 2 should be equal to 3, and of course this checks out. 3 equals 3. So yes, this is the solution to the problem. Remember, when you square both sides of an equation, any solutions that you get are only possible solutions until you perform the check to see that they're actually solutions to the original equation. Okay, let's try another one. The cube root of 5a minus 12 is equal to the cube root of 3a minus 4. We're going to try to solve this equation for a. And in order to eliminate radicals, which of course is how we go about solving these equations, we will not square both sides of the equation, but rather we will cube both sides of the equation. We have a square root, we square both sides to eliminate the radical. With a cube root, we'll cube both sides of the equation. Cube both sides. Okay, the cube root of 5a minus 12 cubed is equal to the cube root of 3a minus 4 cubed. We get just 5a minus 12 on the left is equal to 3a minus 4 on the right. We want to solve for a, so let's subtract 3a from both sides. 2a minus 12 is equal to minus 4. Now we add 12 to both sides of the equation. 2a is equal to 8. Dividing by 2, a is equal to 4. Assuming that our calculations were correct, a equals 4 is the answer to this problem. It is a solution. We do not have to worry about introducing extraneous solutions when we cube both sides. Okay, but just to make sure that our computations were correct, let's check it anyway. See, there's a difference here. Here we are checking just to make sure that our algebra was correct. The other ones we were checking because even if our algebra was correct, we might have introduced extra solutions to the problem. Okay, going back to the original equation, the cube root of 5a minus 12, letting a equal 4, the cube root of 5 times 4 minus 12 should be equal to the cube root of 3 times 4 minus 4. The cube root of 20 minus 12 should be equal to the cube root of 12 minus 4. The cube root of 8 equals the cube root of 8. It checks out. Cube root of 8, of course, is 2. But you could have stopped at that step. Okay, let's try another problem. The square root of 3x minus 2 plus 2 equals x. We would like to solve this radical equation for x. It involves a square root. We're going to square both sides, but before we do that, of course, we will try to isolate the radical. So we'll subtract 2 from both sides of the equation, giving us the square root of 3x minus 2 is equal to x minus 2. Now we will square both sides of the radical of the equation to give us 3x minus 2 on the left and x minus 2 squared on the right. We've squared both sides of the equation. Three x minus 2. Now on the right here, we want to square x minus 2. So it's x minus 2 times x minus 2, giving us x squared minus 4x plus 4. Remember, x minus 2 squared. Right? X minus 2 squared is x minus 2 times x minus 2. By FOIL, it's x squared minus 2x for the minus 4x, and then the plus 4. Okay. Let's combine like terms, see what we have here. Let's subtract 3x from both sides of the equation. Minus 2 is x squared minus 7x plus 4. And then add 2 to both sides of the equation. 0 is equal to x squared minus 7x plus 6. Notice that the equation that we have to solve here is a quadratic equation, a second-degree equation in the variable x. Okay, all the other ones, when we squared both sides of the equation, they were just linear equations. But of course, you can get a quadratic as well. Let's continue our solution over here. We have 0 is x squared minus 7x plus 6. I'll just write that as x squared minus 7x plus 6 equals 0. Just switching the left and the right sides. And of course, to solve this one, this is a very simple one to factor. We've learned how to solve quadratic equations by factoring. All we have to do here is look for two numbers which multiply to 6 and add to minus 7. And the answers are minus 6 and minus 1. Not all quadratic equations can be solved by factoring, but when it does work, it's a very simple way to solve the equation. Checking, we have x squared minus x minus 6x, that's minus 7x plus 6 equals 0. Okay, we have the product of two numbers equals 0. Therefore, we know for sure that either this number, x minus 1 equals 0, x minus 6 equals 0, or this number, x minus 1 equals 0. If the product of two numbers, say a times b equals 0, then for sure either a equals 0 or b equals 0 or both, giving us x equals 6, x equals 1 as two possible solutions to this problem. But at the moment, they are just possible solutions. We must now go back to the original equation and check these solutions. Okay, let's do our check here in the middle. I want to remind you the original equation was the square root of 3x minus 2 plus 2 equals x. We're going to check the x equals 6 and the x equals 1. Let's first work on the x equals 6. We get the square root of 3 times 6 minus 2 plus 2 should be equal to 6. Okay, substituting in 6 wherever we see an x, and we hope that we'll get a true statement. The square root of 18 minus 2 plus 2 should be equal to 6. The square root of 16 plus 2 should be equal to 6. 4 plus 2 should be equal to 6, and of course it is. And it checks out. So x equals 6 is a solution to the original equation. Now let's look at x equals 1, the other possible solution. Going back to the original equation, this time substituting for x the value 1. We get the square root of 3 times 1 minus 2 plus 2 should be equal to 1. Okay, the square root of 3 minus 2, that's the square root of 1, plus 2 should be equal to 1. Or we get that 1 plus 2 should be equal to 1. And of course it is not true. 3 is not equal to 1. The left side is 3, the right side is 1. This is not a solution. The check does not work out. So going back over here to the possible solutions, x equals 6 is a solution. X equals 1 is not a solution. Okay, the only solution is x equals 6. We squared both sides of the equation, and in doing so, we introduced an extraneous solution. And we just followed our algebra through, but squaring both sides introduced an extra solution to the problem, a solution to the squared equation, which was not a solution to the original equation. We detected this by checking each value in the original equation and seeing that the x equals 6 worked out, but the x equals 1 did not. Okay, let's try another example. Solve for x. The square root of 8x plus 1 equals x plus 2. If you would like to try this problem on your own, you can shut off the videotape machine and turn it back on when you've finished. We have the square root of 8x plus 1 equals x plus 2. We start by squaring both sides of the equation. And in doing so, we get the square root of 8x plus 1 squared is equal to x plus 2 squared. On the left, the square root of 8x plus 1 squared just leaves us with 8x plus 1. And on the right, squaring x plus 2, it's x plus 2 times x plus 2, we get x squared plus 4x plus 4. So we have to multiply a binomial by a binomial. It's not just x squared plus 4, it's x squared plus 4x plus 4. Okay, let's collect like terms, see what we have. We can subtract 8x from both sides of the equation, giving us 1 is equal to x squared minus 4x plus 4. And we can then subtract 1 from both sides of the equation, giving us 0 is equal to x squared minus 4x plus 3. Once again, this radical equation gave rise to a second degree quadratic equation. Okay, so let's work on that. Instead of 0 is x squared minus 4x plus 3, I'll write x squared minus 4x plus 3 equals 0. We can solve this quadratic equation by factoring. It's fairly simple to factor it. Two numbers which multiply to 3 and add to minus 4. We have minus 3 and minus 1. Okay, since we have the product of two numbers equals 0, either the first number is 0 or the second number is 0, giving us two possible solutions, adding 3 to both sides, x equals 3, adding 1 to both sides, x equals 1. But these are, at the moment, just possible solutions. Okay, so let's actually check these solutions. And to check, we will go back to the original equation. The square root of 8x plus 1 is equal to x plus 2. First, we will check the value x equals 3. Substituting in x equals 3, we get the square root of 8 times 3 plus 1 should be equal to 3 plus 2. Here we have 8 times 3, 24 plus 1, 25. The square root of 25 should be equal to 5, and of course it is. 5 is equal to 5, and that checks out. Once again, going back to the original equation, this time we're going to substitute in x equals 1, the other solution that we found. X equals 1 in here gives us the square root of 8 times 1 plus 1 should be equal to 1 plus 2. The square root of 8 plus 1, the square root of 9, should be equal to 3, and of course it is. So when we substitute in x equals 3, it works, and when we substitute x equals 1, it works. So both of these solutions, these possible solutions, these solutions to the squared equations are, in fact, solutions to the original equation. Okay, these are solutions. Okay, both of them work. But until we check, they were just possible solutions to the original equation. I'd like to finish off this videotape by doing one more example, this time an example involving two radicals, two square roots. The square root of x plus 5 minus the square root of x equals 1. We would like to solve for x. Now, I have told you that the way to go about solving radical equations is to try to isolate the radical. Here, of course, we have two radicals. And the best way to go about solving this equation is to isolate one of them. Doesn't matter which one you pick. Okay? We can say, for example, add the square root of x to both sides of the equation. And in doing so, we will isolate the square root of x plus 5. Alternately, you could have subtracted the square root of x plus 5 from both sides and isolated the square root of x. The trick is to isolate one of the radicals. Having done that, we now proceed to square both sides. Okay? I isolated the radical, and I then squared both sides of the equation. Now, what's going to happen is that the radical that was isolated will now drop out. Okay, it'll square out. The other one will remain, and we will have to repeat the procedure. We will then have an equation with only one radical. We will re-isolate that. We'll isolate that one and then square both sides again. So with these two radicals, we will have to square the equation twice. Okay, let's do that. The square root of x plus 5 squared, that's just x plus 5. It's 1 plus the square root of x times 1 plus the square root of x. You can work that out on the side, and you'll get 1 plus 2 to the square root of x plus x. All right, now we will try to isolate the radical here. Okay, we will take all terms not involving, aside from this radical, we will subtract all other terms from both sides of the equation and get them over here. Subtracting 1 from both sides, we will get x plus 4 equals 2 the square root of x plus x. And then we will subtract x from both sides. We will get the x minus x gives us 0. 4 equals 2 the square root of x. Okay, you could square both sides in this form, but if you want to completely isolate the radical, okay, we would then divide both sides by 2 to get 4 over 2, that's 2, equals the square root of x. We now square both sides of this equation to get 4 equals x, or x equals 4. Okay? X equals 4 is a possible solution. And we're going to check to see if it is a solution to the original equation. The original equation, remember, is the square root of x plus 5 minus the square root of x equals 1. So substituting in x equals 4, we get the square root of 4 plus 5 minus the square root of 4 should be equal to 1. The square root of 9 minus the square root of 4 should be equal to 1. But the square root of 9, the positive square root of 9 is just 3. Take away the positive square root of 4, which is 2. And of course, 3 minus 2 is equal to 1. So this is the solution. It checks out. X equals 4 is the only solution to this problem. And this brings us to the end of the tape.